Hello guys, so we are continuing the lesson we started, or the topic we started yesterday, graphing rational functions. Yesterday applied to only functions that were given to you in a very specific way. It made it somewhat easy to graph without a calculator, because they had the asymptotes, you could kind of tell what they were. But now we're looking at rational functions that are given in a different way, a more common way to be honest. And that's basically y equals, and then there's a fraction bar there, function on top, function on bottom, and then you're supposed to take it from there. So I'm going to give you a few quick notes. We are going to rely more on the calculator for this one, and then hopefully you'll understand it and that'll be good. So first, points of discontinuity. As always, for points of discontinuity, you set the denominator equal to 0. The results that you get there, the zeros of the denominator, are either going to be holes in the graph or they're going to be vertical asymptotes. For x-intercepts, you set the numerator equal to 0. If it's possible for the numerator to equal 0, and sometimes it's not, but if it is, the answers you get there are x-intercepts. And then for the y-intercept, if there is one, sometimes there isn't, you set x equal to 0. In other words, plug in 0 and work it out. So those are going to be steps that I do through all my examples. For horizontal asymptotes, it turns out that there are 3 possible situations when you have a rational function given to you in this form. Yesterday it was pretty easy. Today it's going to be a little more complex because this form is different. There's differences. So, okay. First, the degree of the numerator equals the degree of the denominator. If you don't know what degree is, I'm going to explain it here real quick. Let me write down a little example. Let's say you got y equals x squared plus 5. Let's say 4x squared plus 5 over 2x squared minus x plus 1. There. So this is a rational function. There's a fraction bar. You have a function on top, function on bottom. The degree of the numerator in this example is 2, and the degree of the denominator is also 2. So degree is simply the highest power. If the highest power of the top equals the highest power of the bottom, then the horizontal asymptote is just y equals, in this problem it's going to be 4 over 2, which leads to y equals 2. 4 over 2 reduces to 2. So the formula is, well, it's not really a formula, it's more of a description. You take the lead coefficient over the lead coefficient. So the lead coefficient here was 4, the lead coefficient there was 2. Lead means first, so the coefficient that's first. If you divide those, that gives you the horizontal asymptote of the graph. And when I do some of these, hopefully that'll be illustrated. The second situation is where the degree of f of x, the top, is less than the degree of the bottom. So for example, if I were to change this example to y equals 4x plus 5 over 2x squared minus x plus 1, now the degree of the top is 1, the degree of the bottom is 2. So the top is less than the bottom. Then the horizontal asymptote is simply the x-axis, or y equals 0. Y equals 0 is the equation of the x-axis. So if the top is smaller than the bottom, the x-axis is the horizontal asymptote. When I say smaller than, I mean the degree. And again, what does degree mean? That's the power. So here the degree was equal, 2 over 2, degree was equal. Here 1 is less than 2, so it's the x-axis, or y equals 0. The third scenario is the degree of the top is greater than the bottom. So this would be like y equals 4x to the third plus 5 over 2x squared minus x plus 1. So as similar as these equations all look, they're different enough that we get these different outcomes. In this situation, the degree of the top is greater than the degree of the bottom. There is simply no horizontal asymptote. And that's a lot to write, so from now on I'm just going to use HA for horizontal asymptote. Hopefully that makes sense. So those are the 3 scenarios. Horizontal asymptote is the basically the fraction you get when you divide the coefficients, that's where the top equals the bottom. Or it's y equals 0, the x-axis, that's where the degree of the top is less than the bottom. Or there is no horizontal asymptote, that's where the degree of the top is greater than the degree of the bottom. Okay, let's get into this. Now, normally, excuse me, when you look at your notes, you got problem 1 here, problem 2 there, 3 here, 4 there, and then I do the evens, they're all down the right-hand side, you do the odds. So this worksheet just printed out differently, or formatted differently, so they're all kind of in a row like this. I've highlighted the evens so I don't get off track, make sure I do the right problems. Okay, so let's look at the directions. For each function, identify the points of discontinuity, the intercepts, that means x and y, the horizontal asymptote, and then sketch the graph. So for points of discontinuity, set the bottom equal to 0. Discontinuity, 3x minus 9 equals 0. Add 9 to both sides, 3x equals 9, divide by 3, x equals 3. So at x equals 3, somewhere there's going to be a discontinuity of some kind, either a hole in the graph or an asymptote. Intercepts. To find the x-intercept, set the numerator, x plus 4, equal to 0. And then solve that. X equals negative 4. So we have a discontinuity at 3, x-intercept at negative 4, the y-intercept. For the y-intercept, you simply plug 0 into the problem. So I made x a 0. It's a funny looking 0. There you go. And this works out to be, well, 4/9. 4/9, which is approximately 0.4. It's 0.4 repeating. So whatever that's worth, 4/9, we'll call it a fraction. So what we're supposed to do, discontinuity, intercepts, horizontal asymptote. Horizontal asymptote, okay. So degree of the top, degree of the bottom. Here, let me write this down, HA. In this situation, the degree of the numerator is 1, and the degree of the denominator is also 1. If there's no power, assume they're 1s. So the degrees are equal. That was the first scenario that I gave up there in the notes. So that equals the what you get when you divide the lead coefficients. The lead coefficient here is 1. The lead coefficient here is 3. So that's 1 divided by 3. So there should be a horizontal asymptote at 1/3, which is a little bit less than a half, right? So right about there. I'm going to have an x-intercept at negative 4. I'm going to have a y-intercept at positive 0.4. 0.4 is a little bit higher than 0.3, right? And my discontinuity is at x equals 3. Okay, I'm thinking I'm making a mistake. Oh, I do see my mistake. Yep, I caught something here. You see that minus sign right there? See how I put a plus sign right there? That was definitely a mistake. Oops. This was supposed to be 3 times 0 minus 9, which gives you negative. Okay, so that y-intercept is not supposed to be right here. It's supposed to be down there, which makes sense, because I know when I graph this, these would have to connect somehow, So there, I saw kind of a mistake. And then x equals 3 is a discontinuity. Now the question, is that a hole in the graph, or is it an asymptote? And we can really use the calculator for that. I know it's going to be an asymptote. If you remember, we kind of studied discontinuity already, and I'm not going to do this on every problem on this worksheet, but you're supposed to factor this and see if anything cancels. If it canceled, it would be a hole in the graph, but x minus 3 does not cancel with x plus 4, which means it's going to be an asymptote. Okay, let's not take too long discussing this one problem. Let's go ahead and get it graphed. So here, y equals, oops, that's a point, equals fraction bar, x plus 4 on top, 3x minus 9 on the bottom. And so my graph, see, do we have a vertical asymptote at 3? Hopefully you can see how we do. There's 3, and if we scroll up, there's our asymptote. Runs really close to the graph. So we got a curve down here, and another one up here. We can check our intercepts. Negative 0.4 repeating, so that's that. Negative 4, there's that. So yeah, everything we did looks just right. Last thing you can do on these problems, of course, is scroll down and check your answer with the answer key. And here's everything just the way we like it. All right, let's go back up and do the next one. And there's not a ton of these. I'll be honest with you, the first time I made this worksheet, I had like twice as many problems, and I realized, wow, that really was a mistake. So I cut it back, and here we go. All right, discontinuity. So for discontinuity, you set the bottom or the denominator equal to 0. When you have a quadratic equal to 0, the easiest way to solve it usually is to factor it. And I think what, x plus 3, x minus 1. Now set each factor equal to 0. And then when you solve those, you get x equals negative 3. There's one discontinuity. And x equals positive 1. So there are 2 discontinuities. Furthermore, if I were to factor this here, it's fairly obvious nothing cancels. So these discontinuities are not going to be wholes. They will be asymptotes. So because I'm going to have to do it anyway, I'm going to go ahead and draw in these 2 asymptotes right now. So negative 3 and positive 1. And yes, you can have 2 asymptotes. Now, intercepts. Let me switch back to red. The x-intercept, you set the numerator equal to 0. Well, the numerator is just the number 1. Can you set 1 equal to 0? No, you can't. So for x-intercept, basically this just means there is none. For y-intercept, you plug 0 into the function. So 1 over 0 squared plus 2 times 0 minus 3. Well, those go away. Excuse me. We end up with negative 1 over negative 3, which is positive 1/3. So there's going to be a y-intercept at positive 1/3, let's say right about there. So no x-intercept. We do have a y-intercept. We have 2 vertical asymptotes. Now the horizontal asymptote. Horizontal asymptote, we look at the degree of the numerator, which, now the degree is the highest power on x. There isn't even an x in the numerator. That means the degree of the top is 0, and the degree of the bottom clearly is 2. So this is a situation where the degree of the top is less than the bottom. Here, maybe I'll write that down. All right, numerator is less than denominator. So when that happens, numerator is less than denominator, the y equals 0, or the x-axis is the horizontal asymptote. So I'm not going to use the words x-axis. I'm going to write y equals 0. I'll consistently do that. So I can now graph a horizontal asymptote here. And now it makes sense as to why there was no x-intercept, because the x-axis is an asymptote. Now all that's left is to graph the curve. Now, there could be a curve up here, or down here, or up here, or down there, or sometimes they curve through like a spaghetti shape. There could be something up here or something down there. And back in the old days, you would just plot points. You'd pick 5, 10, 15 random numbers, plug them in, and see where they fall. But yes, we'll use the graphing calculator. So y equals negative, fraction bar, 1 on top, bottom is x squared plus 2x minus 3. And that negative did not appear, and that's really important. You got to have that negative. So it looks like we have a curve down here, up here. I made sure it went through that x-intercept that I plotted. And a little bit shaky. Had some coffee, maybe got some caffeine going, making my handwriting worse than normal. And there we go. Is that perfect? Nah, but it's good enough. You get the idea. We're going to have all of these answers right, and the graph is really darn close. Not perfection, and I'm okay with not perfection. And just check my answers. and looks pretty good. Now notice here they didn't really graph it so that it goes up like this. And that's just the printing, excuse me, runs out of resolution. So no big deal. All right, let's do the next one. Let's not waste too much time here. So first of all, what's my first step? Well, let's clear that out of there. Discontinuity. For discontinuity, once again, you set the denominator, negative 2x, equal to 0. When you solve that, you just divide both sides by negative 2. So there is a discontinuity at 0, and I do believe that will be a vertical asymptote because that x does not cancel with the numerator. So there's discontinuity. What's next? Intercepts. For the x-intercept, set the numerator equal to 0. To solve this, we can factor it. X plus 3 minus 3, that's a difference of squares. When you set each one equal to 0, you get x equals negative 3, x equals positive 3. So I could jot that down on the graph. There's going to be an x-intercept here, an x-intercept there. For the y-intercept, plug in 0. 0 squared minus 9 over negative 2 times 0. That gives you negative 9 over 0. Now, you're supposed to know this right off the top of your head that you can never divide by 0. That's called undefined. But if it slips your mind, grab a calculator. You see undefined, some calculators say error. That basically means there is none. There's going to be no y-axis, and that makes sense because, no y-intercept because the y-axis is an asymptote. So no y-intercept. Last part of the analysis here is the horizontal asymptote. The degree of the top is greater than the degree of the bottom. Degree of the bottom is 1. When this happens, there is none. There is no horizontal asymptote. So all that's left is to get a graph of this. Y equals fraction bar x squared minus 9 on top, negative 2x. Oops, that didn't work out right. There we go. Negative 2x on the bottom. And we get this shape right here. So how are we going to draw that? Well, just do your best. Don't worry about perfection. Kind of my slogan. Well, all right, that was not very good at all. I'm going to have to... So it curves kind of like this. And it sort of just goes like that. And then this one comes up along this asymptote, hits that, and curves off kind of like that. Now what we do have here, I'll talk about probably tomorrow or the next lesson, we do have something called a slant asymptote. There is a slanted line somewhere in here, and this graph will get closer and closer to that slanted line, but or it's also referred to as an oblique asymptote, but we'll just stop there. I don't want to beat this to death. So let's scroll down, check number 6. And yeah, here we have it. Discontinuity, the horizontal asymptote, or I'm sorry, vertical asymptote is the y-axis. No horizontal asymptote. X-intercepts, no y-intercept. And there's our graph. All right. Number 8. Now look, the directions change here. So identify points of discontinuity. That's the same. Holes. All right, so we got a little tip that there may be holes in these graphs. Intercepts, horizontal asymptote, and the domain. Sketch the graph. I forgot that I put the domain part in there. Oh well, we can handle this. All right. First, points of discontinuity. Well, all right. Here's what I'm going to do on these problems. They're going to be quite a bit more complex, and because we have holes, we do have to look for things that cancel. So before I do anything, I'm going to go ahead and factor the top. So I could factor out a negative x here. That's going to be x plus 2. Factor the bottom. Factor out an x. That's going to leave me x minus 4. And if you factor each one before you do anything else, it'll make some of the work easier. I didn't do it on any of the other problems. I could have, because I did do some factoring eventually anyway. So just a little tip, when they get more complicated, like this one, like this one. Factor them first. All right, discontinuity. So for discontinuity, you're supposed to set the bottom equal to 0. Since the bottom is already factored, I can just write x equals 0, x minus 4 equals 0. I get x equals 0, and then if I add 4 over to that side, x equals positive 4. So there's my points of discontinuity. Wholes. Well, if you look at the original function, these two x's would cancel if you're simplifying that, which means that this one is a whole. So x equals 0 is going to be a hole in the graph. That means the other one is going to be an asymptote. All right, so that's discontinuity. Well, what else was there? Discontinuity, holes, intercepts. So for the x-intercept, we're going to set the top equal to 0. Well, the top is, I didn't mean to do that. The top is already factored. So if I set that equal to 0, I have to set negative x equal to 0, and I have to set x plus 2 equal to 0. Well, this one I just divide both sides by negative 1, I get x equals 0. This one I have to subtract 2, x equals negative 2. And then I'd say, okay, these are my x-intercepts. But wait. Well, first of all, I did a horrible job circling those. This one we've already determined is a hole. It can't be a hole in the graph and an x-intercept. So if we know that that's a hole, it's not an x-intercept. So I'm just going to cross that out. So there's only one x-intercept right there, which if I suppose I could plot that. I could maybe even try to do it correctly. All right, y-intercept. For the y-intercept, we plug 0 into the function. If I plug 0, I can do that into the original function right here. I plug 0 into that. I get negative 0 squared minus 2 times 0 over 0 squared minus 4 times 0. That ultimately gives me 0 over 0, which, remember, you cannot divide by 0. Divide by 0. That's undefined. So for y-intercept, there is none. No y-intercept. Interesting. Let's do horizontal intercept, or horizontal asymptote, rather. Sorry. Right, is that next? Horizontal asymptote, yes. So what's the degree of the top? Negative, I'm sorry, 2. What's the degree of the bottom? 2. So remember, when the degree of the top equals the bottom, here, I'm going to put that down here, numerator equals denominator. When that happens, y equals, and then we make a fraction out of the lead coefficients. The lead coefficient here is negative 1. The lead coefficient here is positive 1. That's negative 1 over positive 1, which turns into y equals negative 1. And then finally, the domain. Well, domain is always going to be very easy. I think that's why I put it in here. Domain is always, always very easy. All you have to do is write down all real numbers. Then you can either use the word except and then the discontinuities. And it doesn't matter what type of discontinuities they are. 0 and 4 were discontinuities. So are all real numbers except x equals 0, x equals 4. Or you can do all real numbers, comma, x not equal to 0, x not equal to 4. So those are two different ways to do the domain. After I graph it, I'll scroll down and see which way the answer key uses. So time to graph it. Y equals fraction bar negative x squared minus 2x on the numerator and x squared, darn it, x squared minus 4x in the denominator. So, first of all, there is a vertical asymptote, and it appears to be at 4, which was a discontinuity. So I can, I'll switch colors here, sketch in my vertical asymptote there. Does there appear to be a horizontal asymptote? Well, yeah, we figured there'd be a horizontal asymptote at negative 1, and that kind of makes sense here when we look at the graph. So horizontal asymptote right there. Now we predicted a hole in the graph at 0. Remember, you can trace this with your finger, and when you get to there, you see that there is a hole in the graph right about there. Oh, I'll do that in red. So to sketch the rest of the graph now, we've got a curve piece down here, a curve right here, but when it hits that point, there's a hole in the graph, and it looks like that. Wow, that's a lot. It's pretty heavy duty. You're doing some real heavy math analysis here. All right, so let's check our answers for number 8 and see if we got all the components. So 2 discontinuities, 0 is a hole, horizontal asymptote, x-intercept, no y-intercept, all real numbers. So they don't use the symbol for all real numbers. They use the except, the word except. So that's cool. There it is. All right, one more. Again, a good way to do these problems, these more complicated ones, is do all the factoring first. So this one is x, 2 times 1, plus 2 minus 1. The bottom here, you can factor out a 3 first, which is probably going to make that a little simpler. And then, so we factor out a 3. You got x, 3 times 1, minus 3 plus 1. Is that right? Yeah, I think it is. Now, this is really freaking me out because if both of these were x minus 1 or if they were both x plus 1, they'd cancel. There would be a hole in the graph. It's close, but they don't cancel. So there should be no hole in the graph unless I've factored wrong. So because I have a little doubt in my mind, a little question, I'm gonna skip down here. Okay, no hole in the graph. Good. Okay, right on track. Okay, so let's do discontinuities. For discontinuities, set the denominator equal to 0. So it's already factored, so I set x minus 3 equal to 0 and x plus 1 equal to 0. I get x equals 3, x equals negative 1. So there's my discontinuities. Holes in the graph, I just said there are none, and we checked it, so that's good. None because nothing cancels. What comes next? Intercepts. X-intercept, set the numerator equal to 0. X plus 2 equals 0, solve that. X minus 1 equals 0. See what I'm doing? I'm taking this and setting them both equal to 0. So here I get x equals negative 2, and here add 1 to both sides, x equals 1. So I should have 2 x-intercepts. You know what? There's a lot of work here, a lot of steps. I'm going to check each step, and that might be a good way for you to go about a worksheet like this. So x-intercepts 1 and negative 2. I got those right. We got that. Okay, good. 1 and negative 2. Let me make that more clear. There. Okay, y-intercept. We plug 0 in to the whole original function. So 0 squared plus 0 minus 2 over 3 times 0 squared minus 6 times 0 minus 9. Well, all those zeros go away, and we end up with negative 2 over negative 9, which is 2/9, which is about 0.2 repeating, isn't it? So right about there. Let me check y-intercept. Or, well, just 2/9. Okay, so discontinuity, holes, x-intercept, y-intercept. What's next? Horizontal asymptote? Yep. Horizontal asymptote. Degree of the top equals degree of the bottom. That means the horizontal asymptote, so numerator equals denominator. That means it's going to be y equals, and then I make a fraction out of the lead coefficients. Well, the lead coefficient here is 1. The lead coefficient there is 3. So 1/3. If I draw a horizontal asymptote at 1/3, it's just going to be barely above that point right there. And I'm not doing a good job. That's way out of scale, but it'll be good enough. And you know, while I'm at it, since those discontinuities, well, no, they're not holes. If they're not holes, they've got to be vertical asymptotes. So I can get that drawn in there. And I'm getting a little off track. I was going to be checking my work as I go. Horizontal asymptote, there it is, 1/3. So the domain, again, all real numbers except the two discontinuities, -1 and 3. So that's our domain. Let's make sure I did that right. Yep, except -1, 3, and then draw the graph. And for this, it's just using the graphing calculator. Y equals fraction bar x squared plus x minus 2 over 3x squared minus 6x, 6x minus 9. And did I have x-intercepts? Oh yeah, I just didn't draw them. So -2 is supposed to be an x-intercept, and +1 is supposed to be an x-intercept. So we get something like this, something like this, and then like so. And my picture doesn't look great, doesn't look perfect, but looks good enough. All right, so I'll leave it there. Try the odds on your own. Check yourself. You might want to check yourself after each step like I did. I don't know. Be sure to show your work. As you can see, there's a lot going on here. So a lot of work on each problem, but only 5 problems total, and you are using Desmos to help you with the graphing. So hopefully it doesn't feel like an overload of work. If you have any questions or comments, let me know, and otherwise I will talk to you later.